Today we're going to be reviewing some factoring techniques from Algebra 1, and I'm also going to show you some new factoring techniques. Let's start with the most basic type of factoring, and that's factoring out the GCF. And again, GCF stands for greatest common factor. Some things to keep in mind is that sometimes the greatest common factor is a number, like 5 or 1/2. Sometimes the greatest common factor is a variable, like x, or even a product of variables, like x squared y. And sometimes the greatest common factor is a binomial, like x plus 3. So watch for different kinds of greatest common factors. Let's look at example 1. In this case, you can see that the greatest common factor is both the 3 and both terms contain x squared. So I'm going to pull out 3x squared. Taking out 3x squared, that would leave me x squared for my first term and 16 for my second term. And then I would be finished. Remember that sums of squares can never be factored, only differences of squares. So x squared plus 16, that's as far as we can factor. Let's take a look at example number 2. This time you'll notice that the thing they have in common is a binomial. If you factor this binomial out of each term, you'll notice that what's left is 3x minus 4. So in example 2, this would be it. We're finished factoring right here. Let's look for other unusual types of GCFs, and that might be fractions. You might not be used to taking out fractions, but taking out fractions can be really useful so that the remaining factors are only integers. So in this case, we're going to take out the 1/3. One-third y divided by 1/3 is y. The other one's a little tricky. 1/3 times what number gives you 5? 1/3 of 15 gives you 5. And if you're not sure if you've done it correctly, you can always distribute it back out and double check and make sure it works. Alright, the next one is also a little bit tricky. We're going to look at the GCF first as just the binomial. We'll take that out. Then we're going to look at this guy right here, and we're going to take out this fraction, just like we did in example 3. So this is going to be y plus 1. We'll take out a 1/5. That'll leave me with 4y minus 10. So you might be wondering, where did I get the 10 from? Well, remember over here when I wanted to get a 5 and I had to think about 1/3 times what number would get me 5? I'm doing the same thing over here. I've got a 1/5. If you distributed this back out, you'd have to think of 1/5 times what number could get you back to here, this 2. So the answer would be 10. Then I'm looking at this guy again, and I'm noticing that 4y and 10 both have 2 in common. So I can also pull out that 2. So this 1/5 is going to become a 2/5. And then 4y minus 10 will become 2y minus 5. And now I'm finished with example 4. So this is the type of factoring that you probably are most familiar with from last year, or in Algebra 1, I should say. And this is trinomial factoring into two binomials, so what we sometimes call reverse foiling. And there are lots of different techniques, but the one you probably maybe have the most familiarity with is maybe the diamond or the X factoring. In this problem, we take the last term, 6, and the middle term, negative 5. We're trying to think of two numbers which multiply to give us 6, but add to give us negative 5. So in this case, it would be negative 3 and negative 2, and this becomes x squared. Oops, not x squared. X minus 3 times x minus 2. Those ones are the easiest ones to look at. In example 6, this problem is a little more difficult because the leading coefficient is not 1. Whenever the leading coefficient isn't 1, we have to do these problems a little differently. Instead of looking for two numbers that multiply to give me 6, I actually multiply the leading coefficient times the constant before I think about the product. So I'm thinking of two numbers which multiply to give me negative 30, or negative 5 times 6, but add to give me negative 13. Those two numbers are going to be negative 15 and positive 2. Now, unlike problem example 5, you can't just take these numbers and plug them into the binomial. What you're actually doing is splitting the negative 13u. So this problem becomes minus 5u squared minus 15u plus 2u plus 6. So this process is only taking me from 3 terms to 4 terms. Now I want to do something called factoring by grouping, where I'm going to take the greatest common factor out of each one of these pairs. From the first pair, I can take out negative 5u, and I'm left with u plus 3. From the second pair, I can take out 2, and I'm left with u plus 3. Now you may notice that these guys have a common binomial, u plus 3. That's my GCF here. When I take out u plus 3 from each of these factors, I'm left with minus 5u plus 2. And that's the factored form of example 6. Now example 7 and example 8 are what are known as perfect trinomial squares. So what is a perfect trinomial square? It means that it's a product of squaring a binomial. So a plus b squared is going to be a squared plus 2ab plus b squared. So what I'm looking for is I'm looking to see if the first term is a perfect square. Check, check. I'm looking to see if the last term is a perfect square. Check, check. And I'm looking to see if the middle term is twice the product of their square roots. So let's check that. In example 7, this would be x times x. This would be 5 times 5. Is the middle number twice this product? Yes. So this is just x plus 5 quantity squared. Let's take a look at example 8. It seems like a hard problem because you've got a fraction in it. But if I stop to check to see if it's a perfect trinomial square first, it's actually fairly easy to factor. Is the first a square? Yes, it's y times y. Is the last a square? Yes, it's 1/2 times 1/2. Is the middle term twice half of y? Yes, it's 1y. So this is y plus 1/2 quantity squared. When you have a trinomial, it's always worth checking to see if it's a perfect trinomial square before you try other factoring methods. So we already talked a little bit about factoring by grouping. Factoring by grouping, we work whenever we have exactly 4 terms. It doesn't always work, because remember, not every problem is factorable, but when I see 4 terms, the first thing I always want to think about is factoring by grouping. I always think of factoring by grouping a little bit as double dating. What I mean by double dating is that we're going to pare these four down into two dates, okay? So you've got four people going out together. Imagine that they're splitting off like they're on a double date. So in the first grouping, we're looking to see if these first two have anything in common. Do x cubed and 3x squared have anything in common? Yes, they have x squared in common. So I'm taking the GCF out of the first two numbers, and I'm left with x minus 3. Then I'm going to look at the second group, and I'm going to take the GCF out of this group. Do 3x and 9 have anything in common? Yes, I can take out 3. Once we take the GCF out of each group, we notice that now we have a GCF, which is a binomial. So when I take x minus 3 out, I'm left with x squared plus 3. And again, remember, you cannot break down the sum of squares, only the difference of squares, so I'm finished when I get here. Let's look at example 10. Again, I'm going to break them off into double dates. Take the GCF out of the first. That would be x cubed. And then in the last one, you might say, well, x squared plus 2, they don't have anything in common. In this case, we would say, well, they have 1 in common. When two numbers are relatively prime, in other words, they don't share any common factors, they actually do share a 1, so we would just pull a 1 out. Like the previous problem, we can see that these terms now contain x squared plus 2 as their GCF. So we'll pull x squared plus 2 out of both terms, and we're left with x cubed plus 1. Now it looks like we should be finished with example 10, but we're actually not. Turns out that this guy right here is the sum of cubes. And the sum of cubes can be broken down even more. We can factor the sum of cubes. So we're going to do that in the next part, and then I want you to come back up to example 10 and break down x cubed plus 1. So let's look at the sum of cubes. So when you factor the sum of cubes, there are two important formulas. There's a formula for the sum of cubes and a formula for the difference of cubes. And there's a couple noticeable patterns. First of all, you'll notice with the sum formula that when you have a plus here, you have a plus here. And when you have a minus here, you have a minus here. So the first binomial will contain the exact same sign as the problem that you start with. Then you'll notice that this guy right here and right here, these are opposite signs from the original problem, right? Whereas the first two had the same sign. So what do I really need to do to use these formulas? I need to find the cube root, and then I need to plug the cube root into the formula. So let's look at example 11. What's the cube root of x cubed? Okay, it's x. What's the cube root of 27? It's 3. When you're plugging into this equation, we're going to start by keeping the same sign. Okay, so far so good. Then we're going to take x and multiply him by x squared. That gives me x cubed. Right? And I'm going to take negative 3 and I'm going to multiply him by 3 squared or 9. That gives me negative 27. Then I'm going to multiply these guys together and use the opposite sign in the middle. Okay? So remember, this one was the same sign. This one's the opposite sign. This was x squared. This was minus 3 squared. And this guy was the product. So let's do the same thing with example 12. This is 2x cubed. This is 1 cubed. Keeping the same sign, 2x times 4x squared is how I'm going to get 8x cubed. 1 times 1 is how I'm going to get 1. I'm going to take the product and put that in here. Remember, this guy was the same sign. This guy's going to be the opposite sign. This guy was 2x squared. This guy was 1 squared. And this guy, again, was the product.